So hello students, today we'll begin with the magnetic effects of electric current. So we have covered up some important topics already on this chapter. The last we studied was the heating effect of electric current. So today we will study the magnetic effect of electric current. As I told you, around 70% of this topic is devoted to magnetic effects of electric current, right? So if the title is well understood, from the title itself you could understand, right? Effects of electric current is the title of the chapter. So one of the effect is magnetic effect of electric current. The title tells you that electric current has the ability to produce magnetism. Students, now it is vice versa. Magnetism can produce electricity and electricity can produce magnetism. It is both ways. That's why we call this as electromagnetism, right? Or electromagnetic studies. So these are basically connected. Now what you're going to see over here, these experiments are all in relation to magnetic effect of electric current. Later in this chapter, we'll also be learning about your working of a motor, working of a generator. All these are based on electric current and its effects, right? So now we will have a look at this. Now students, what you are seeing over here in both these experiments, in fact, this experiment particularly tells you or proves that whenever current is passed through a conductor, a magnetic field is generated in the region around the conductor. Now students, the scientist Hans Christian Ørsted, the scientist, right? He was the one to discover that whenever current is passed through a metallic conductor, as you see here, whenever current is passed through a metallic conductor, there is a magnetic field that is produced in the region surrounding the conductor, and that was observed with the help of this experiment. In fact, in your own simple way, in your home too, you can perform this experiment. If you have a small compass needle, you can take it near any wire which is carrying electric current in your house, or with the help of a battery or a cell, you take a wire and connect it from the positive to the negative and bring the magnetic needle or compass needle near it. You will observe some type of movement or deflection, right? So please remember one very important thing. The magnetic effect of electric current was discovered by Hans Christian Ørsted. So our today's discussion will be around this topic itself. And you know, every magnetic field, like you studied before, like a bar magnet has a magnetic field in which there are magnetic lines of force. Magnetic lines of force is actually a path followed by the north pole in a magnetic field. You learned about in the previous standards. So right, let us now first talk about what happens when an electric current is passed through a conductor, right? So here you have an arrangement that is shown over here. This arrangement is showing you over here. You have a conductor AB. Can you see? AB is a wire or a conductor which is connected to the positive and the negative terminals of a cell, right? This is the battery or the plug key to switch the current on and off. And here you have a magnetic compass needle. All of you know that the magnetic compass needle comes to rest in the north-south direction. Now supposing your plug key is open. Open means in the sense the current is not on. Then this magnetic compass needle will rest in the north-south direction, right? Now let us check what happens when we insert the plug key. The moment you insert the plug key, that means the circuit gets completed and a current will start flowing from the positive terminal to the negative terminal. Now when you put on the plug key, you have to observe what happens to this compass needle. The compass needle, you will see that it gets deflected. Can you see like this? It is like that. Now that it will get deflected. Deflected means it will change its direction. As soon as you insert the plug key, the magnetic needle, the north pole will turn like this, right? Can you see this? So you take out the plug key and the magnetic compass needle from its deflected position will come back to its original position. Again you insert the plug key, you will find that the magnetic needle gets deflected. That means this is very clear that, see, what happens is when you are putting the plug key, a current is flowing and that current is causing a deflection in this magnetic compass needle, right? When you remove the plug key, the magnetic compass needle comes to its original position because there is no current flowing in the circuit. So this experiment, right, clearly proves that when a current is flowing through a conductor, there is some magnetic field which is generated in the region around the conductor, which is causing this magnetic compass needle to turn in a particular direction, right? Now you can see here there is a positive pole and you can see the north pole turning in this direction. Supposing we interchange the polarity. Changing the polarity means you are reversing the terminals. Supposing I make this terminal as the negative and this terminal I make as the positive, right? So if we change the polarity, so this becomes negative, now this becomes positive, then what will happen? Instead of the direction of the current being like this, now the direction of the current will get reversed. So direction of current now throughout will get reversed, right? Similarly, that means the current will flow now in this direction, right? So the direction of current changes and it will flow like this. So when you find that the current reverses its direction, so the direction of current is from positive to negative, so you will find now instead of going like this, the compass needle will turn in the reverse direction. So the compass needle will turn like this, exactly in the opposite direction as before. So actually the magnetic compass needle gets deflected in the direction of current. But what is more important to observe, right? The very fact that the magnetic needle gets deflected when you start the current by putting on the plug key, the very fact that when current is flowing there is a deflection, that means there is a magnetic field produced the moment current starts flowing, which is proved by this compass needle changing its direction. When you remove the plug key, it comes back to its original position. So in this experiment, the deflection of the magnetic needle when current is flowing through this proves that whenever current is flowing through a conductor, there is a magnetic field generated in the field in the region around the conductor. Now every magnetic field, students, has its own magnetic lines of force, right? But it depends upon the conductor. Like here now you are going to see the patterns of the lines of force, of the magnetic lines of force. Now what are these magnetic lines of force? Magnetic lines of force is the path followed by the north pole, right, in a magnetic field. You have seen in a bar magnet, maybe last year, this is the bar magnet, right? So if you have a bar magnet here, let us say this is the north pole and this is the south pole, and you have a compass needle over here, right? So when you bring the compass needle, you will find that the north pole will keep on changing its direction like this. So this is the north pole. You bring it here, the north pole will be like this. You bring it here, the north pole will be like this. So the north pole keeps on changing its direction in a magnetic field, and when you join the points of the north pole traveling, you will get some lines like this. You must have seen this diagram. These curved lines are magnetic lines of force, right, which exist around a bar magnet, because around a bar magnet there is a magnetic field, and in this magnetic field there are magnetic lines of force that begin from the north pole and end on the south pole. So there are many such magnetic lines of force around a bar magnet. Similarly, when current flows through a conductor, right? So this wire itself acts like a magnet, and there is a magnetic field produced in the region around the conductor, and because there is a magnetic field, there are magnetic lines of force in the region around the conductor. Now students, here there is a very important observation. I told you when you change the polarity, the direction of the north pole will change, right? Now when the positive, you saw in the first case the needle got deflected like this. In the second case, when we change the terminals, it got deflected like this. Another very important point is, if the current is kept constant, when you keep the current constant and as you bring the compass needle farther away from the conductor, you will find that the angle by which the compass needle gets deflected, right? This angle, see, here it gets deflected, supposing by this angle over here. If you take it far, then instead of getting deflected by a huge angle, the angle will be only so much. So that means, supposing now this is here and this compass needle is at a distance, right, from the conductor, then the deflection will be only so much, right? If it is near the conductor, then the deflection increases. So that means the magnetic field is stronger in the region near the conductor, right? Because as the conductor is near, the magnetic field is very, very strong. So this compass needle will show greater deflection or greater change in direction. If this magnetic compass needle is put at a distance from this conductor, the angle by which it changes its direction will be less. That is because the intensity of the magnetic field at a point at a distance from the conductor is less. So as you move away from the conductor, the strength of the magnetic field produced by this conductor because of current flowing through it is less. And if you go near the conductor, the strength of the magnetic field produced due to current flowing in it will be more. On the other hand, you can see, keep this compass needle at the same position. Don't change its position. Don't take it near or far. Only you increase the current by changing the number of cells. So you will find that at a given point, right, if I increase the current flowing through this conductor, if the value of current flowing through the conductor increases, this magnetic needle will get deflected by a bigger direction. If the current flowing is small, then the deflection will be small. If the current flowing is more, then the deflection of the magnetic needle will be more. That means the magnetic field, right, produced in a region around the conductor is inversely proportional to the distance. As you go away from the conductor, the strength of magnetic field decreases. You come near the conductor, the strength of magnetic field increases. And the other point is that as you increase the amount of current at any given point, this is a fixed point. So as you increase the current flowing through this conductor by increasing the number of cells, if you increase the number of cells, the current flowing through this conductor will increase. So if this magnetic needle is fixed over here, you will find that as you keep on increasing the amount of current flowing through the conductor, the magnetic needle will get deflected by greater direction. That means its shift will be more. The angle by which it changes its direction will be more. So students, this you have understood now from this experiment of Hans Christian Ørsted, that when current passes through a conductor, a magnetic field is produced in the region around the conductor, and at a given point the strength of magnetic field is directly proportional to the current flowing through the conductor. What is the meaning of directly proportional? If the current increases, the strength of magnetic field will increase, right? If the current decreases, the strength of magnetic field produced will decrease. And as you move away for a given value of current, you don't change the current now, for a given value of current, if you come near the conductor, the strength of magnetic field is strong, and if you go away from the conductor, the strength of magnetic field decreases. These are two important learning points that you should know. Now, as I told you, like you saw that the magnetic lines of force of a bar magnet, they are close continuous curves from the north pole to the south pole. Now let us study the magnetic lines of force, yeah, for the magnetic field which is produced by a current carrying straight conductor. So this is, let us say, a current carrying straight conductor. I'll name it as P and Q. So this is a current carrying straight conductor, straight wire, like this ruler, right? It's a straight conductor, not curved, nothing. It's a straight conductor. So we are going to study the magnetic lines of force. What will be the pattern of the magnetic lines of force, whether they will be closed curves or what, that we are going to study. So this is an experiment. What they have done in this experiment is that they have taken a insulated copper wire, a thick insulated copper wire PQ. Then a cardboard is taken, a hole is made in the center of the cardboard, right? And this wire PQ is pushed through that hole, and the ends of the wire are connected across the terminals of a cell. You can see one end is connected to positive, the other end of this wire is connected to the negative, and you have a plug key, right? Now what is done is, this cardboard is over here, right? Now what they do is, before putting on the plug key, they take some iron filings. You know what are iron filings? Powder of irons, or pieces, small pieces of iron are kept near this wire. They are kept very near this wire, they are just kept. Then what happens? The plug key is inserted. That means you switch the current on. Now you know from this experiment, as you switch the current on, there is going to be a magnetic field which will be generated in the region around this conductor, right? So the magnetic field is going to be generated because current is flowing through this conductor PQ. Now because the magnetic field is generated, you just observe this cardboard, you just tip it, just tip the cardboard like that. When you tip the cardboard, those iron filings, you will find they arrange themselves in concentric circles like this. You know what are concentric circles? Circles having a common center. So you will find the iron filings forming a pattern like this. You can see these dotted lines. So the iron filings will form a pattern of concentric circles. So this experiment gives us many conclusions. From this experiment we can conclude many things. I will tell you what. The first thing you can conclude is that when current is flowing through the conductor, a magnetic field is produced. Because here also you can keep a compass needle. As soon as you pass current through this wire, you will find that the magnetic compass needle is undergoing some type of change in its direction, right? That means when current is flowing through PQ, a magnetic field is produced, causing deflection in the magnetic needle, and the magnetic field has magnetic lines of force. So this current carrying straight conductor has magnetic lines of force which are in the form of concentric circles. Can you see? And this concentric circles, students, is not formed only at this point. At every point along the conductor, every point you will have the magnetic field in the form of concentric circle. At every point you will have the magnetic field in the form of concentric circles. At every point, not only here. Here, because the iron filings are there. If you shift the cardboard down, the same thing will happen, right? So you will find that for a current carrying straight conductor, if you have a current carrying straight conductor, then the magnetic lines of force of their magnetic field are in the form of concentric circles, right? For a bar magnet, they are not concentric, they were closed curves starting from the north pole and ending on the south pole. Now students, one more important observation can be made over here. Supposing you increase the current by increasing the number of cells over here. If you increase the current, what is going to happen? That you will, and you tap the cardboard. If you increase the current, you will find that these circles, they come closer to each other. The circles will come closer to each other. Because the strength of magnetic field increases if you are going to increase the current flowing through this conductor by changing the number of cells. When you increase the number of cells, the current flowing will increase and the concentric circles, they come closer because the magnetic field generated due to current flowing in this coil becomes stronger and stronger. If the current is weak and you tap this, the concentric circles will spread far away. So students, these two experiments very clearly tell you that whenever current flows through a conductor, a magnetic field is produced in the region surrounding the conductor, and the strength of the magnetic field is directly proportional to the magnitude or quantity of current, right? And the strength of the magnetic field is inversely proportional to the distance. I have already explained that to you. And for a current carrying straight conductor, the magnetic lines of force are in the form of concentric circles. This is what you have to remember. You can be asked, what does this experiment indicate? For example, what they do is they give you the diagrams, and from the diagrams they will ask you, what does this experimental arrangement talk about? What effect of electric current does it talk about? Who discovered it? And write a few points on it. So they may show you these diagrams and ask you, what do these diagrams depict? Do you know that this diagram, what it depicts? What does this diagram depict? First and foremost, this diagram depicts that when a current is passed through a straight conductor, right? Not only a straight conductor, but in this case it is a straight conductor. So you will say that when a current passes through the conductor PQ, a magnetic field is produced in the region around the conductor because the magnetic compass needle shows deflection. Then you will say that the second point you will say that the magnetic lines of force for a current carrying straight conductor is in the form of concentric circles. Then you will also make a point saying that if the current through the conductor is increased, if the current passing through the conductor is increased, the intensity or the strength of the magnetic field will also increase, which can be seen by the concentric circles coming nearer. So if you make these points, that's enough. For this, if you are shown this diagram, you will say that this diagram is an experimental arrangement which was done by Hans Christian Ørsted, right? And this experimental arrangement says that when a current is passed through the conductor AB, then what happens? A magnetic field is produced in the region around this conductor AB, which is shown by the deflection of this magnetic compass needle, right? Then you can say that as the amount of current passing through the conductor is increased, the strength of the magnetic field also increases, which can be seen by an increase in the angle of deflection of this compass needle. Then you can also say that as one moves away from the conductor, the strength of the magnetic field decreases. That means the strength of the magnetic field is inversely proportional to the distance from the conductor, right? So these are some of the important points, students, which you have gathered today. Then there are some other important thing. Today the last point is the right hand thumb rule. Now the right hand thumb rule is giving you the relation between the current flowing through between the direction of the current flowing through a conductor and the direction of the magnetic field which is produced due to current flowing in the conductor. So I will state the right hand rule and I will show you, right? So just look at this. Students, just imagine, now what I am talking about is the right hand thumb rule, right students? So imagine that this is a current carrying straight conductor which I am holding in my right hand. So this is a current carrying conductor which is held in my right hand. For better visibility, I am standing like this. Can you see here? So this is a current carrying conductor which is held in the right hand with my thumb which is stretched along the length. My thumb is stretched along the length and the fingers are curled around the conductor. Can you see this very clearly? My thumb is stretched along the length and the fingers are curled around the conductor. So the right hand thumb rule says like this, right? Imagine that you are holding a current carrying conductor in your right hand. If the thumb is stretched in the direction of the current, or if the direction of the thumb gives you the direction of the current, then the direction of the curled fingers gives you the direction of the magnetic field. What does it mean? That supposing this is the conductor and current is flowing in this direction, my thumb is pointing upward, na? So if the current is flowing in this direction, then the magnetic lines of force are moving around this. See, like this. they are moving in an anti-clockwise direction. Clockwise it would be like that. So anti-clockwise direction, right? In this way. If I am holding the conductor like this, then if the current is flowing like this, the magnetic field is going to be like this, right? If I am holding the current in a different way, if I am holding the conductor like this, then if the current direction is like this, then the lines of magnetic force will be like this. I hope you understood the right hand rule. The right hand thumb rule, it is known as. The right hand thumb rule gives you the relation between the direction of current flowing in a straight conductor and the direction of the magnetic lines of force which are formed, right, due to current flowing in this conductor. So what does the right hand thumb rule state? Imagine that you are holding a current carrying conductor in your right hand with the thumb stretched along its length. If the direction of the thumb gives the direction of current, then the direction of the curled fingers will give you the direction of the magnetic field. So students, for today, this is the learning that we have done. We will be learning more on the magnetic effects of electric current. Today we learned about a current carrying straight conductor, right? The pattern of magnetic lines of force. Here we saw they are concentric circles. Tomorrow we will learn about, you can read before that, you will understand. We will study about the magnetic lines of force of a current carrying loop, circular loop, L-O-O-P. You study there, you will find that every point on the loop as well, right? At every point on the loop, the magnetic lines of force are in the form of concentric circles. Please read that activity for magnetic lines of force in case of a current carrying loop. It is the same as this, only thing is this is a straight conductor and those will be loops. In case of the loop, as you increase the number of turns in the loop, the magnetic field will increase. And the magnetic lines of force there on every point of the loop will be in the form of concentric circles. So students, today this is all that I had to discuss. Hope you had a clear understanding of the lecture. In our next lecture, we'll try to improve the visibility and the focus of the board. We are trying this as an experiment today, and I'm sure that you would have understood properly with this, because many a times most of my explanations are you're seeing the board but you're not seeing me. So we have made an attempt. We have brought this board over here from class and we have done it. So today it was a trial basis. When the technician comes, I'll be organizing it in a better way, maybe tomorrow. But till then, students, take care of yourselves, stay happy, stay safe, and do your studies regularly. Meet you tomorrow during the next lecture for further discussion on this topic. Till then, students, thanks and bye to all of you.